This is a chessboard, and these are coins. If you place 1 penny on the first square, 2 pennies on the next square, 4 pennies on the third square, 8 on the next square, and keep doubling the amount of money of the previous square to get the next square, what we are getting here is what we call as a geometric sequence. And the sum of all this money is what we call as the geometric series. In today's lesson, we are going to talk about geometric sequence and geometric series. To put our lesson in perspective, let's say we have this situation. Professor Hector just won in a math competition. For his prize, the king of Tribo Mathematica asked him to ask for any prize. You want a trip to the moon? A new Tesla car? Scholarship for assistant in German academy? He can ask for anything, and the king will give it to him. But to everyone's surprise, Professor Hector just asked for 1 penny to be placed on the first square of the chessboard, 2 pennies on the next square, and then double that to get 4 pennies, and then double that to get 8 pennies, and he just requested that all these squares of this chessboard be filled with these coins until the 64th square. The question is that a wise decision? Let's check. Mathematically, we can represent the situation this way. Let n be the position of the square from the first square, the second square, up to the 64th square. And the amount in number of cents is 1 cent, 2 cents, double that to get 4, double that to get 8, double to get 16, 32, until the value at the 64th square. And in terms of notation, we can write it this way. Let a sub 1 be the first term, and the value is 1 cent. For the second square, we have 1 times 2 to get the 2. For the third, we have 1 times 2 times 2, which is 4. For the fourth is 1 times 2 times 2 times 2 to get 8, which is this 8. We can also write this way. A sub 1 is the first term. The second term is equal to the first term, a sub 1, multiplied by the common ratio. When you divide 4 by 2, you get 2. You divide 8 by 4, you get 2. You divide 16 by 8, you get 2. The common ratio here, which we call as the R, is equal to 2. This is the first term times the R value, which is raised to the first here. For the third term, or for the third square, we have the first term times R, or we can write this as R to the second power, or R squared. And then to the fourth, and then in the fourth square, it's the first term times R raised to the third. If you're going to follow this pattern, what would be the representation for a sub n? Notice that when you have a subscript here of 2, your exponent is 1. When you have a subscript here of 3, the exponent is 2. Subscript 4, the exponent is 1 less than whatever is the number here. So if you have a subscript of n, this exponent must be 1 less than n. So we just copy a sub 1 times r, and we raise that to n minus 1. Because the relationship between this subscript and that exponent is that the exponent is always 1 less than this subscript. So we therefore can write the nth term this way. This is now the nth term notation. So, following now this formula, how much money will Professor Hector get at the 64th square? Notice that we are not getting the sum of all the money. What we are trying to get is just the value of the money at the 64th square. So using now the formula, a sub 64 equals the first term, which is 1 cent, times the ratio, which is 2, raised to n minus 1, which is 64 minus 1, or 63. So we now have a sub 64 equals 2 raised to the 63rd, because the first term is 1, 1 times that value is still the same value. Now using our scientific calculator, this is the value that we are going to get. The value at the 64th square is 9.2233720369 times 10 raised to the 18th power cents. So this is in terms of the number of cents. Or in dollar value, that is this number times 10 to the 16. Or that is equal to 92 quintillion. This is thousand, million, billion, trillion, quadrillion, and quintillion. That's how big the amount is. But this is not it. Professor Hector wants to get all the money in all those 64 squares. So what we are going to do is get the sum of all those money. In order to do that, we are going to derive some formula. When we get the sum of the sequence, the result is what we call as the series. So we are computing now for the geometric series. The geometric series is the sum of the geometric terms. So let's represent the terms of the geometric sequence as a sub 1. The next one is a sub 1 times the common ratio r. The next one is a sub 1 times the common ratio raised to the second until a raised to n minus 1. because we multiply this by r on the second term. So we have n minus 1 here. If we get the sum of all these terms, what we have is a series. In order to derive the formula, this is the strategy that we're going to use. Let us multiply s, whose terms are these terms, by r. So this s becomes r times s. This a sub 1 becomes a sub 1 times r because you multiplied by r. This one, a sub 1 times r, is multiplied by r, so that r becomes r squared, and the same explanation for the other terms. So at this point, this n minus 1 becomes a sub 1 times r raised to n because we multiplied by r. And then this dot 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 says there are terms in between, and I inserted this term prior to the last term. There's also a term prior to that one, and that represents that. So what we have after that is this one. Let us subtract s minus rs. So s minus rs. Subtract these two. That means term by term, we are going to subtract all of this. But I want you to notice that this one are just the same. A sub 1 times r, a sub 1 times r. The next one are also the same. A sub 1 r squared, a sub 1 r squared. And the process continues. There must be a term over here, and then this one also will be the same. And what is left is this one. But since we are subtracting, every term here must be minus. So what we are left therefore is the difference here is equal to this one, a sub 1, and the remaining term here, which is minus a sub 1 r to the n, which is this one. And so we have now a more simplified form. There's a common factor s here, so what we can do is factor out the common factor s. So we have s divided by s is 1, rs divided by s is 1 minus r. There is also a common factor here of a sub 1. So factoring that out, we have a sub 1 equals divide this 2 to get 1, divide this 2 to get r to the n. And finally, we can now solve for s, which is the sum of all these terms. So finally, s is equal to this term divided by 1 minus r. Or another form of that is a sub 1 times this ratio. This is now the formula for the geometric series. We can find the partial sum of a geometric series if we apply this formula. And in some cases, this formula will work even if we have what we call as infinite series. And that happens when the value of r is between 0 and 1. So applying now this formula to find the total amount of money Professor Hector will get from all these 64 squares, so we now have this computation. We are looking for the partial sum at s sub 64. So we just replace n with 64, and r is 2 because we doubled the value from 1 cent to 2 cents to 4 cents to 8 cents and so on. Now the first term is we start with 1 cent. So whatever computation we have here is in terms of the number of cents. It's not the dollar value, but the number of cents. So you have any number multiplied by 1 is 1, so we can just ignore this one. We have this 1 minus 2 raised to 64 over 1 minus 2, which is negative 1. And using our scientific calculator, we will arrive at this value, 1.8446744074 times 10 raised to 19 power. That is in terms of number of cents. And in dollar value, that is equivalent to 184 quintillion approximately. And to put this in perspective, the world economy as of 2020, that means the aggregate economy of 194 countries, including all the economic activities in these countries, only total to $138 trillion as of year 2020. But in this scheme, the Professor Hector thinks he is getting way more than the combined value of all countries' economy. That's how smart this proposal is. And this is the characteristic of geometric sequence. It can have what we call as accelerated growth when r is more than 1, and it could have an accelerated decay when r is between 0 and 1. Now, let's have another example. In this case, we have what we call as infinite sum. We are asked to find the sum of 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32, and then continue this pattern up to infinity. So in this case, what is our r value? Notice that from 1/2, we multiply it by 1/2 to get the 1/4, multiply by 1/2 to get the 1/8, multiply by 1/2 to get 1 over 16. So our r is 1/2. And our first term is this term, so we have 1/2 as well. And then we are going to get the sum of this, but the problem is we are not going to stop. We are going to continue this sequence up to infinity. But you will notice that the value becomes smaller and smaller and smaller as we progress. And at certain point, that increase would be very minimal, that no matter how much you extend the number of terms, it will reach what we call as a limiting value. So applying now the formula that we derived in the previous discussion, we have the sum of n terms equals the first term times 1 minus r to the n over 1 minus r, where n is approaching infinity. But one thing that you have to observe here is this 1/2 raised to n as n approaches infinity. When you have 1/2 raised to n, that is just the same as 1 raised to n over 2 raised to n. And 1 raised to any number is 1, no matter how big that number is, so 1 over 2 raised to n. Now, as n approaches infinity, this n becomes very, very big number. So you are going to raise 2 to that very, very big number. This denominator would be very, very big. But since it's a denominator, you divide 1 by a very, very big number. The value of this would be very, very small. That becomes negligible, and we just think of the limit of this value as n approaches infinity to be 0. So basically what you have here is 1 minus 0, which is 1. 1 minus 1/2 is positive 1/2, and copy the first term. Now this one we can manage. So you have 1/2. 1 over 1/2 is 1 times the reciprocal of 1/2, which is 2 over 1. And 1/2 times 2 over 1 is 1. So therefore, of this infinite convergent geometric series is 1. And this is the value that we use as reference when we computed the value of number e up to certain decimal number precision.